Okay. So yes, we can laugh. Take a moment to laugh about that. And okay, so let's do antiderivatives and indefinite integrals. That's the first thing that we do. These are pretty straightforward, right? So actually the order in which we learn these is generally the order that you usually take. That's the approach you take when you're trying to do an integral. So let's just take one of these problems, and let's just practice it. Let's try this one because word problems are always fun, right? So a particle moves along the x-axis so that its acceleration at time t is a of t equals 8 minus 8t in units of feet and seconds. If the velocity of the particle at t equals 0 is 12 feet per second, how many seconds will it take for the particle to reach its furthest point to the right? Okay. There's two ways to do it. One is using an indefinite integral, and the other is using a definite integral using FTOC. I say FTC, but either way is fine. On the AP exam, they'll accept both. I don't know if you guys have seen some of the scoring guidelines, but you're allowed to take because think about it. What you're doing in a definite integral is you're finding net accumulation of change, right? What you're doing in an indefinite integral is you're finding that, but as a more general version of it. You're finding a plus c. What the definite integral does is it takes care of that plus c because you're essentially doing the plus c and then minus c, because when you take the definite integral, you're taking the upper and the lower bound, right? So it goes away and you're just finding net change. However, if you want to do it just antiderivative way, let's go ahead and see what happens. So we wanted to find time, but we need to know velocity, right? We're trying to find velocity.
Yeah.
What are we trying to find? Let's see.
You first have the velocity equation, and then you have to find it. I actually had a question about this one. I forgot about it. Okay. Yesterday.
Okay, so velocity as a function of time is going to equal the integral of acceleration of time, right? And this would be 8t minus t squared over 4, correct? Or sorry, 4t squared. I'm sorry. 4t squared, correct? Plus c, of course. Now you use the fact that v of 0 equals 12 to figure out your c. So if you just plug in zeros, you know that your c is going to be 12. So I'm not going to waste time and show that. You can just know that. 4t squared plus 12. So that's your velocity. Now, how many seconds will it take for the particle to reach its furthest point to the right? What does it mean for the particle to reach its furthest point to the right? What does that say about velocity?
It has to be a velocity is 0, right?
It happens when, yes. Why is velocity 0? Because, or it could be undefined, or it could be like one of those undefined cases, but usually you won't have that. Because when x is at its maximum, that's when velocity will be equal to 0 because it's turning point, right? Okay, so let's just go ahead and set this equal to 0. And if we factor out a 4, let's see, 4 times 2t minus 2, wait, 4 times 2t minus t squared. I wrote this out weird, but whatever. Plus 3, and then if you factor this, that's I'm gonna actually factor out a negative because that'll make it easier. That'll be a minus. Let's factor t plus 1 times t minus 3, I believe. That means your solutions are -1 and +3. You likely don't, in problems like these, you likely don't start at -1. You're going to start at 3, or you start at 0, so you'll get 3 seconds. If you wanted to really check, then you could do the table where you figure out, okay, you can do your intervals. I do the number line instead. I say, okay, let's draw a number line for myself. I have -1, I have 3. To find v of t, let's just plug in a number like 0 into here. If I plug in a number like 0 into here, will I get a positive or negative number? If I plug in a number like 0, I'm going to get a positive number. So this interval is positive. And then this interval, if I plug in something like 4, that'll be 16 times 4 is 64. 4 times 8 is 32.
Wait,
32
what
minus
are you
16.
doing?
Oh, I'm finding whether velocity is positive or negative.
Oh, okay.
This is just to
really
check my answer.
confused.
Yeah.
Okay. Sorry, that sounded really aggressive.
No, I'm sorry. No, you're fine. You're fine. Don't worry about it. And ask questions. Please interrupt me if you have questions. I don't get offended by that.
Also, Zachary's asking if you could let him
Oh,
know.
I'm so sorry. I just saw him. Okay. And then you'll find that this is negative. So that tells you that your velocity increases and then decreases, which makes sense, right? Because it goes to the right and then to the left. Neha, what's so funny? I understand why Miss Raja always gets on. Okay. All right. Hopefully that makes sense. Does anyone have any questions about that?
In the answer key, just like it was like a of 3 is like less than 0, but like aren't we trying to look at like velocity? So like why is it like
it's using the second derivative method, because when you take the second derivative, if you know it's concave down at x equals 3, then you know that velocity. Yeah.
Okay.
Either way is fine. Yeah, it's just different ways of doing it. Okay. All right. Any more questions about this one? All right. Let's try one more from here, and then we'll move on to the next lesson. Which one do you guys want to do? Anyone in particular? Perhaps a word problem, because I know those are harder. But any particular one? Or would you rather move on to the next one? Move on to the next lesson? Okay, let's do that. Oh wait, just close current tab. I don't want to close the BC one yet. We'll go over those in a bit. Okay. Next one is U-sub, right? Did we do U-sub next? I don't have these in order. U-sub is next? Okay. All right. Which one do you guys want to do? Any? Okay. Let's do something like, these are always fun. Okay, let's do something like this one. Okay, so let's think about this. When can you use U-sub? That's something that we get confused a lot, is because sometimes we'll see fractions and we'll say, oh, that's automatically partial fraction decomposition. But sometimes U-sub is the better option. Here, obviously, we don't see fractions. But when do you use a substitution? When? What do you guys think? Rishi, when do you use a U-substitution? Gautam, anyone? Trudy, Maham, anyone say?
When you can't find an integral without like using some like I don't know how to like explain this.
Sure. Yes, but then I'd say, well, you could also argue the same thing for integration by parts. You can't find an integral the normal way. So what? There's a specific time when you use it. Go ahead, Mom.
You have like U, and then if du is if you can identify du or like a constant in front of du, then you know that you can do U-sub.
Exactly. U-sub is used when you can do some sort of substitution, and then if you take its derivative, that's also part of it, and then that'll like clean it up. And that takes skill, because sometimes it's tricky, because we know that this problem is a U-sub problem, but sometimes if they just give you an integral, you might not know that it's a U-sub problem. So you have to think, okay, I see a secant x and I see a tan x. That seems promising, because I know that there is a function whose derivative is sec x tan x, right? I know that the derivative of sec x is sec x tan x, right? So why don't I do something to help myself? Let's break this, because I know that we might want to use a sec x tan x. I'll write that separately. And then because I've pulled one out, this will now become sec squared x, correct? Now what I can do is I can do a U substitution, because now I can say U equals sec x and then du equals sec x tan x dx, correct? And why is this helpful? Because now I know this whole thing is du, and I know that this is u squared. So now I can write this as the integral of u squared du, and this is an easy problem. This is u cubed over 3 plus c. Substitute back in, you'll get sec cubed x over 3 plus c. Does that make sense? So it takes skill, and it takes just recognition of the things. Okay, now let's try one of these real quick, a definite integral. Let's try something like this one real quick. Yeah. And I'm picking this one on purpose. If you just saw this, you might be tempted to use integration by parts, would you not? Right? You might be tempted. Rishi, since you were annotating, I'm gonna pick on you this time. Rishi, can you unmute yourself?
Yeah.
Okay. Why would we use u sub here instead of integration by parts?
So I think essentially you would use U-substitution to write it in a simplified way to kind of get everything into one term, so that way you can easily take its integral.
Can you like specifically to this problem, why would that be the better option than trying to take x as a function and then e to the minus x squared as another function? Why do you think, first of all, what would probably be the best substitution? What should we substitute?
I think 2 minus x squared would be our u in this case, right? For
U
number
equals
10.
negative x squared? Oh, sorry, I'm doing number 5.
Oh, okay. For number 5, I would think x as u. Because
that would
I
be
remember,
problematic. If you take,
I remember this rule that like I watched on a video
Okay.
called Liotte.
okay,
And
that's okay. Hold on. This is what I was going to. Liotte is for integration by parts, and honestly, Liotte works sometimes and it doesn't work sometimes, so that's not a reliable method. And it's okay. It's helpful. It's a helpful tool, but it doesn't always work. And this was my point, was that in functions like this, you're tempted to use integration by parts because it looks like it's 2 functions. The reason why you use u sub here, does anyone know? Does anyone want to say? Because if you say, you'll better your understanding as well. Zachary, Curran, anyone can chime in if they'd like to.
I mean, I did this one and I got like negative half du equals x dx, and I saw that x dx was like there, so I could plug it back in. For me, it just worked that way, and I knew
Okay.
that e to the power of x derivative is just e to the power of x, or
Exactly.
integral.
Sure. So you need to make the recognition that if I take the derivative of this, I'll get x. Don't worry about constants. 2x, I can just pull that out. But the thing is, the derivative of x squared is x, and I have an x here, so I can make a u substitution. Now, if this was something like x cubed, then you might be in a little bit more trouble. Would a u substitution be possible? Possibly. You would have a 3x squared, and then you'd have another x, which might make it a little complicated, and then you might have to use integration by parts, and that's a different story. But here, you can see clearly that if I take the derivative of this, I'll get this function, right? That's why we want to use u sub here. So let's say u equals negative x squared, du equals minus 2x dx. That means someone in the waiting room, yes, okay. Now that means that if I take, how should I set up my u substitution? Anyone? Curran said it, right? Curran, do you want to repeat that?
Yeah, I divided the other side by halves, or I multiplied it by half essentially. So it said negative half du equals x dx. So yeah, if you
Okay.
expand it out, you get negative half integral of e to the power of u du.
E to the u du.
Yeah.
Now, there's 2 ways of doing these. Some people will write x equals 1 to x equals root 2. They'll find the antiderivative in terms of u, then substitute back x it, and then do the root 2 and 1. That's too complicated. The easier thing to do is just say what u is. Now we're in the u world, so why not just write your numbers in the u world? If I plug in x to my, x equals 1 to this, then I'll get -1. And if I plug in root 2, I'm going to get -2. So now this is -½ If I take this, the antiderivative of this, that's just e to the u. And I am going to evaluate it at -2 and then -1. So this is e to the -2 minus e to the -1. And you can, if you want to expand this out, you can write this as 1 over 2e squared plus 1 over 2e. Correct? Okay. I think we're good with U-substitution. What do you guys think? Good with U-substitution? Any questions about U-sub? The bigger thing to understand is not that it's an easy process. The bigger thing to understand is when is it more beneficial to use U-sub versus integration by parts or partial fraction? In same idea. Here you might be tempted to do partial fraction decomposition, but you always want to see if you can do U-sub first. And the reason when you can do U-sub is when, once again, if you take something's derivative, it'll match whatever's something. You see what I'm saying? If you take something's derivative, it'll be somewhere else in the function, and that'll eliminate everything else. And if you still have things left over, then you might need to consider partial fractions or integration. Okay, good. I think U-sub is good. Let's move on. What's next? Definite integrals. Okay. Let's do a word problem. If they have word problems. I think this is what we need to do. Yeah, this is what we need. What do you guys think? Because I think definite integrals make sense, right? We just did one. It makes complete sense. You just take the antiderivative and then you evaluate it at b and then subtract the evaluation at a. And then you get your integral, right? I think the problem is here. Would you guys agree that this is where we're kind of lost? Okay. Yeah. Okay. Let's just think about this. What you're doing is you're taking the function, right? You have some function f of x. What you're doing is you're starting with your lower bound and you're adding I minus 1 because I is equal to 1. If this was I equals 0, then you wouldn't have that, but yeah. So just you're starting with I minus 1 times delta x and then multiplying that whole thing by delta x. Let's think about this visually, because visually this just makes more sense. Okay, so let's say this is a, and let's say this is our last number b. And let's say this is delta x. This is delta x, this is another delta x. What I'm doing is I'm starting my summation from I equals 1 going to n. I start at actually f of a, if you think about it. What am I doing here? I'm starting at f of a, right? I'm not starting at f of delta x, because what happens is 1 minus 1 is 0 times delta x goes away. So I'm actually starting at f of a times delta x. So what I just calculated was the left Riemann sum for this. I calculated this value for this one. Next, I'm going to calculate when I equals 2. 2 minus 1 is 1. That means I'm going to do 1 delta x of f of a plus delta x. F of a plus delta x is this point, and I multiply that by delta x. Then that's this integral. And then same thing you'll do for 2 delta x, and then once you're done, you would have reached b. And then you add those areas together, and then you get your approximation for integral. What this says is let's take the limit as this n approaches infinity. And what that allows us to do is we're going to take smaller and smaller and smaller pieces, and then that way they'll add up to the exact value, which is the integral. Okay, so a's will always be our first number. I minus 1 is the index, right? It's referring to that index. And then delta x is delta x. It's your change index. Okay, so let's think about this. Delta x here is just 3 over n. What is a plus delta x times I? That would be this portion right here. That's the 2 plus 3 over n I. What is f of x? F of x would then be what?
X squared or n squared. X
So
squared.
x squared, right? F of x equals x squared. Because this is the function. It's a plus delta xi, whatever it is, squared. Okay?
So I have a question.
Yeah.
What is the purpose of like writing it like this?
Because this helps you to, okay, because essentially this, you're actually not calculating the Riemann sum. What you're doing is you're calculating the integral. So I need to write this in integral form so I know what they actually it's asking.
No, I mean, like, why do they write it as like the limit of the summation of, like, what is the purpose of doing it?
Because originally we didn't have integrals. We had used Riemann sums to approximate areas. So there came a time when we realized, when Leibniz and Newton, they started doing their work with calculus, and they realized, you know, this is the more efficient way of doing it, using an integral and thinking about it as the inverse of the derivative. And then we needed a way to connect the idea of Riemann sums as areas under curve to an exact, more exact way of doing it. So that's why we needed to do this. Okay. And then what's the value of A? That's just 2. What's the value of B? This is kind of where I get lost sometimes. So what would be the value of B?
B, like B minus 2 over n equals 3 over n. So B is 5. Yeah.
5 because 3 over n. Sorry, can you say that one more time?
Because 3 over n. B minus 2 over n.
B minus A over n, right?
Yeah. I mean, no, over n.
Oh, sorry. B minus A over n will equal your delta x, correct?
Yes.
Okay. So, and once again, I'll just say this out loud for my sake as well. What we're doing here is we're finding delta x using the fact that we're taking B minus A and dividing it by intervals and by n intervals. Okay, that's what delta x is. And we found, like Alina said, n was just n. We don't need to worry about that for right now because delta x is 3 over n. So if you solve this, n's will go away. You'll have B minus A equals 3. We knew that A was 2, so that means 5 minus 3, 2 is 3. Okay, that means B is 5. Now, using this information, now we know what our integral is. It's from 2 to 5 of f of x dx. F of x was negative x squared, and you just put a dx. And now what I can do, I don't know how to calculate this. Like, does this make any sense to me mathematically how I can do this? No, I can't do that. So now that I have it in a form that I can use antiderivatives, now I know that this will be negative x cubed on 3 evaluated at 5 and 2. You can pull up the negative if you wanted to. Okay, good. Let's do one more from this section. Let's do one of the ones that was like Miss Brown's. Yeah, it could also be this one. Yeah, so let's look at one of these. First thing is, let's kind of figure out what this sum is asking for. What is this sum? This is the limit. Okay, can someone walk me through this? I just want to make sure we're getting this. That's all.
Which one are we doing?
Number 14.
Are we doing A or
A
B?
first, and then we'll do B, because you can do it both ways. Ria, do you want to try? I don't. Yeah, if you're not comfortable, that's completely fine. I'm just. Gautam, you want to try? Anyone? Anish?
I'm like completely lost. So
You're lost on these?
hoping
Okay.
someone else would,
Sure.
walk through.
Anish?
I
Zachary?
just joined, so I'm a little bit lost.
Okay. Neha, do you want to try?
Yeah, sure.
Okay.
So 1 over n is delta x.
Okay.
And so A should be.
Sorry, can you enlighten us on that, and why do you think delta x is 1 over n?
Because the whole thing is multiplied by 1 over n.
Because
right?
we're doing the rectangles, right? So we wanted to like multiply by. Okay, good. So we know that that's
and
true.
then-
Okay.
And then so we see in the actual like thing, sorry, we see that it's 1 over 2 plus, and then the thing in the parentheses changes, so that's, delta x. And so it's delta x times I actually. So so it's 2 plus what's in the parentheses, so that means 2 is A,
Good.
because that's like the starting point.
Mhm.
And so from that, we can also find B, which is basically B minus 2 over n equals 1 over n, so B should be 3.
Good.
And so the actual equation, since A plus delta x times I would be like the whole x, it should be 1 over x for f of x.
Exactly.
And so the integral should be like the integral of 1 over x dx from 2 to 3.
2 to 3, exactly, perfect. As 1 over, you can write dx over x here. Yeah. If I wanted to write this in summation notation, because sometimes they'll ask you about that, how would I do that? Same principle. You take this, and you take the integral from I equals something. We don't know whether it's a 0 or a 1 yet, but we'll figure that out soon. To n of f of x, of f of a plus, right? So we'll take 1 over 2 plus 1 over ni. And I seems to be starting at 1, correct? Okay, I seems to be starting at 1. And then we have this whole thing multiplied by delta x, which is the 1 over n, correct? Did I do this properly? Set this up. This is what we're doing. You need to be able to switch between the two forms and just think about it conceptually. What is going on? Think about it as rectangles if you need to. That helps. The other option is to start with this function, 1 over x plus 1. Whenever it says show in AP Calculus, whenever it says the word show, what you're doing is you're doing a proof, okay? Show means proof, okay? So you're going to do a proof that this integral equals this integral. There's a few ways you can do it. Perhaps one is to simply calculate this definite integral and then calculate this definite integral and then say that the two are equal. That's one way. Let's do a more elegant way, perhaps. Let's try and think about this. How can we do this? I can view this function. Delta x will still be 1 over n, but let's think of this function as f of x is equal to 1 over x plus 1. Okay? Okay. If we do this, then I need to make this match one of these forms. How do I do that? Well, I know that it'll be 1 over a plus 1 over a plus, or it'll be 1 over a plus delta xi, right? So we know we're starting at 1 probably, or could be 0. Let's just say we start at 0. I equals 0. If I starts at 0 and we're going to n, that means whatever we have in the bottom, it'll be instead of 2 plus, now we're starting with, actually, what would this be? Plus 1? Sorry, I'm lost. Can someone?
If we're doing something like this, can't we just like solve for it?
That would probably be the easier way.
This seems very extensive.
It's yeah. My concern though is sometimes they'll be like on the AP exam, it might be I don't know. I feel like you would need to know how to do it this way. It might not. It's like 1 point maybe, but still, I mean, it might be important. So, I think what you would do is simply just say f of a plus delta x. Okay, that means if this is our x, that means we're going to plug in a plus delta xi, correct? Yeah. Okay, good. Sorry, I was just.
The answer for like needing assistance. She did some like
U-Substitution. Yeah, a lot of people do that. That doesn't make sense for me. You can do it because then what you do is u equals x plus 1 du equals dx, and then you can just, call that 1 over u, integral from 1 to 2 of 1 over u du, and then you know that because now you're in the u world, you just plug that in. 1 over 1 plus 1 is 2, and 2 plus 1 is 3, and now you had what you had before, right? Okay, that's the easy way to do it. I don't think I was making myself clear in the other version, but I think I get it now. So f of x is equal to 1 over x plus 1. That means if I wanted to take the limit, let's use that formula that we had above, of the sum from I equals 1 or 0, we don't know that yet, to up to n, and then we're going to take f of a plus delta xi, and then we're going to multiply this whole thing by delta x. That means this is the sum, the limit from n of n approaches infinity of this sum. I know delta x is still 1 over n. That's not going to change. Delta x is not going to change. It's still 1 over n. And you'll have 1 over a plus delta xi plus 1. So the plus 1 is just being added here. And what we can notice now is that a instead of a is now going to be 1, because this is the first number is a 2, so it'll be 1 plus 1 is 2, and then delta xi will still be 1 over n I, but we need 2 plus 1 over n, right? That means I actually would need to be equal to 1. Yeah, and that's pretty much it. And then now you can use this form to go back to the integral. Okay, that was very complicated, but do you see, kind of get the conceptual understanding of it, like what we're doing? We're just trying to match the formula. Okay, are we good with definite integrals for now? Okay. All right. What do you guys want to do next? Ftc and Mvt or integration by parts?
Can we do the integration by parts, like the easy method?
Yes. I know everyone's been wanting to. Okay. Okay. For this, I'm going to use the whiteboard because I'd like to show you. There's 3 cases that you need to know essentially. Okay. Zoom share. Okay. All right. So the first case is something like this. Let's take the integral of x squared sine of 3x dx. First option would be to think, can we do U-substitution? No, right? Because there's no way I can try and take u to be x squared and then du would be 2x, but it wouldn't work, right? We can see clearly that U-substitution won't work. So now we try integration by parts. This is called the tabular method or the DI method. You're doing the same thing as u and dv, but what's nice is you don't have to keep writing u and dv over and over, and it just cleans it up. So what you're going to do is you're going to write d and then an I, and then you're going to write a plus, minus, plus, minus, plus, minus all the way down. Okay? You're not going to need many, but just trust the method right now. It'll make sense later. Okay. Now we have 2 laughers now, which is fun. Anyway, I'm just giving you all a hard time. Okay. Now you have to think, which of these can I differentiate easily and which of these can I integrate easily? In this case, I can do both. But our goal is to stop at 0, and I'll show you why. Let's just take for now, trust the process, just take this to be x squared, and let's take this to be sine 3x. And this is where you might have used your Liotte method, but once again, there's no need for Liotte when you figure out how to do it this way. You have x squared and sine 3x. If I differentiate this, I get 2x. If I integrate this, I'm going to get minus 1/3 cos 3x, correct? And then if I differentiate this, I'm going to get 2. If I integrate this, I'm going to get...
Isn't it just -3 cos 3? No?
No, because if I take the derivative of this...
Oh, wait, yes.
Yeah,
Never mind.
yeah.
My
Okay.
bad.
No, you're fine. And then the next one would be minus 1/9 sine 3x, correct? And then the next one, if I differentiate 2, I get a 0. And then this right here will actually be 1 over 27 cos 3x, correct? As soon as your D column gets to a 0, you can stop. This is where I stop. So here's the trick. Whenever you have an integration by parts problem and you see a polynomial, you'd want to put that in your D column, because you know you can, once you integrate it over and over, you'll get to a 0 eventually. And with this DI method, as soon as you get to a 0, you can stop. Okay, so now what I'm going to do is I'm going to take the diagonals. Okay, so if I take the diagonals, x squared times this, I'm going to get x squared, or negative 1/3, negative 1/3 x squared cos 3x. The next one will be plus, because this is a negative. This is why we wrote the plus minus plus minus. Negative 2x times the negative 1/9 will be what? It will be plus 2x over 9 sine 3x. And then we do the next diagonal, which is plus 2 over 27 cos 3x. And then you have your plus c, and you're done. Why? How does this compare? You're doing the exact same thing. It's just making it more efficient. It's kind of like reduced row echelon form, where you're doing the same thing as elimination, but you're just not writing it out. Because what we did was we took u equals x squared, and we took dv. Oh, whoops. And then we took dv equals sine 3x, and you just did it over and over. And rather than having to rewrite the integral each time, you were able to do it in a more efficient process. You see what we did? And the reason why this is a minus should make sense, because remember, the formula for integration by parts is uv minus integral of v du, right? So that's why we did minus the integral of v du.
Is this a good method if you know you have to do the integral like many
Over and
times?
over? Yes, for sure. This is the best way to do it.
But like if it's just like one time, wouldn't it could be like you could do either, right? It'll be
You
the
could do
same.
either. I still prefer this just because it's universal and it works. But either is fine. Okay, this
So
is
would this
case
be-
1. Okay, sorry,
So
go
would
ahead.
this be the answer? Like this?
Yeah, right here. This is the answer. Done.
Okay.
What if you have e to the x? We will get there. We will get there, Anish. That's the next part. Okay. So this is rule 1. Case 1 is when you have a 0. Okay? Go ahead and remember that. If you have a polynomial, you have a 0. Case 2. Let's take the integral of x to the 4th ln x. We're not at the e to the x yet, but we'll get there. Same idea. You're gonna use your the di method. Do a plus minus plus minus. I'm going to take x to the 4th because I cannot integrate ln x. I know, I need to put, sorry, I did this wrong. I know I cannot integrate ln x, so this is going to go in this column, and I put an x 4th here. Now I'm going to get a 1 over x, and then if I integrate this, I'm going to get x to the 5th over 5. Now I know if I keep doing this, this is going to be endless. However, that's the second rule, is you stop when you can take the integral of a row. As soon as you can take the integral of the product of a row, you stop. And this is the same thing in your normal integration by parts. So now what this is just x to the 4th ln x minus the integral of 1 over x times x to the 5th over 5, which would be x to the 4th over 5 dx. And this would be x to the 4th ln x minus x to the 5th over 25 plus c. And you might be asking, why did we use the di method here? It doesn't really help. You're right. You would be right. It doesn't really help here. You're doing the same thing. Are you guys starting to see the parallels between di method and your formula? It's essentially doing the same thing. If there were more steps, then this would be helpful. But this is the second rule: is whenever you can take the integral easily of the product of a row, you stop. Okay, that's case 2. Case 3 is what Anish was bringing up. What if you have something like the integral of e to the x sine x dx? Whenever I have this, Doesn't this consume it won't consume lots of time. For the ones that have like 4 steps of integrals, this saves you so much time. Like you can easily go through these very quickly. It's just because you haven't practiced this yet that it seems very challenging. But if you practice this a few times tonight, you'll immediately get the hang of it. It's one of the easiest methods. I'm going to take e to the x here. I'm going to get sine to the x, and I'll show you a motivation why we do that. Because in case 3, as soon as you see the same function twice, you stop integrating, because you can use that rule where you double both sides and you can divide by 2. So derivative of this is e to the x, integral of this is minus cos x, derivative of this is minus sine, or integral of this is minus sine x, and this would still be e to the x. And I'm going to stop right here because I see that I repeated sine x. Whenever you repeat, you're going to stop. Okay? You're going to stop because now I know that this is equal to, I'm still going to take my diagonals. I'm going to get e to the x. So actually, it'll be minus e to the x cos x plus e to the x sine x. And then I have minus integral of e to the x sine x dx. And you know that if I add this to both, if I take this and I put it on this side, it'll become 2 that. And then if I divide both sides by 2, I get that plus c. That's your answer. Did that make sense or no?
Can you repeat everything you just did?
Yeah, sure. Did you get this, what we did up to here? The e to the x, e to the x,
Yeah,
e
I
to the
got
x?
that. It's
You
just-
got the sine x minus. So this is case 3. In case 3, you stop when you have the same function twice. Why? Because remember, if you have that, we took the diagonals, e to the x times minus cos x, minus e to the x times minus sine x is plus e to the x sine x. And then for the last one, you take the row, because we are not going to take it again. But whenever you take a row, you have to use the integral sign. And it's minus e to the x sine x dx. And this time, and the reason why we stopped was, notice that because you have the same thing on both sides, I can add this to the other side and I'll get 2 integral of e to the x sine x dx equals minus e to the x cos x plus e to the x sine x, right? Now I can just divide both sides by 2, right? If I divide both sides by 2, now I got what I wanted. I actually got the original function that I wanted, and then you have to put your plus c. Does that make sense, Trudy?
Yeah, I got it. Thank you so
Okay,
much.
let's do some more problems, and then it'll make sense. Okay, let me open up her integration by parts problem, and you can see how easily this works. And I'll just go through a few of them. Go ahead.
Before we continue, I have a quick question.
Sure.
On the AP problems, for for some of them, for the delta x, instead of using like b minus a over n, they get it from using the average somehow. And I'm just kind of confused on like if you look at, like, I was working on Shruti with, I think Shruti knows what I'm talking about. We tried to use b minus a over n to find delta x, but that's not what gave us the delta x she was using.
For which one?
I think a good example would be like question 2 on the AP problems, page 3.
AP problems on net change AP problems?
Yeah.
Okay, can we do that in a bit? I want to finish up integration by parts first. Okay,
Yeah.
and we'll do that right after. Okay. Okay, does someone want to try using the DI method on this one? I'm just gonna, I'll just go through the first few because I think you're still kind of confused about it, which is understandable. So I know easily that e to the x is something I can integrate. X is something that's gonna get me to 0, right? Because remember, that's case 1. Whenever I get to 0, I can stop. So I'm gonna take x, if I integrate that one time, that's 1. Or sorry, take it differentiated, that's 1. If I take its derivative again, that's 0. If I have e to the x, then I'll take e to the x again, and then e to the x again, because that's its integral over and over. All right, bye, Alina. Okay, and if you take the product of these two, you're gonna get x e to the x. Remember, you're taking the diagonals, x e to the x minus e to the x, and then if you integrate this is just 0. That's why we can stop when we have a 0, and then plus c. You see how easy that was? No u, you didn't have to write down what u was, what dv was, what v, and then du, all that. You didn't need to do all that. Easy. Okay, next one, x cos to the x. Now, what do you guys think? Should I put x here or should I put x here? Should I put it under D or I? Will it be easier to differentiate x or what do you guys think? Current. What do you think?
Yeah. Okay, I think D, right? Because it would go to 0. Is that?
Yes, Ria
think
also
it's
said the same
default.
thing. Good. So if you put x here, and you put a cos x here, this will be a 1, 0, easy. Derivative of, or integration of this is sine x, and then you'll have minus cos x, right? And then you would say, okay, now take the diagonals, you'll get x sine x plus cos x plus c, and you're done. Good. So that's some good practice for the case 1 problems. Okay. You understand?
Can you try it on? Sorry. Can you try it on one of like the more complicated
Yeah,
problems?
of course. Which one would you like to do?
I'm not sure which is the most complicated.
You want to try something like this, maybe? No, this
Yeah.
one's still easy because you would still get 2x and a 0,
Um,
a 2 and then 0. That would be easy.
yeah. Okay.
What? You know, these are all easy when you think about it. Like once you start using the DI method, let's try something like this.
Okay. Yeah. Actually, that one, she took out. Of
Oh,
the,
because yeah, I know why. Because you'd have to do partial fraction decomposition for this one.
oh, okay.
Yeah, you'd have to break this up into quadratic factors, and then you would use integration by parts. Okay.
What about like sine squared x?
Oh, sine squared x, or this one, or sine squared x?
Either one is fine.
Okay, we'll do both. Let's start with this one, sine square root x dx. Okay. Let's do our di. Okay. I think we might need to do a u-sub here. Yeah, u-sub is not negotiable. That di method doesn't help with that. So if you were hoping to get that out of di method, that's not going to work. But u equals root x. Let's take du equals 1 over 2 root x dx. So that means dx equals 2 root x du. So I can rewrite this as integral of 2 root x sine u du, but I need to be in my u world, so I know that root x is u, so let's just replace this with the u here. So I have 2u sine u du, and once again I just plug it into my integral. I think 2u is probably easier here. Sine u will probably be easier here because I know with 2u I can get to a 0, and that will be the easiest way to do it. 0. And this will be minus cos u, and this will be minus sine u. So your integral will be minus 2u cos u plus 2 sine u plus c. You can plug in your u's. This will be minus 2 root x cos root x plus 2 sine root x plus c. Good? Okay. Let's try sine squared x real quick. Integration of sine squared x dx. First thing I'm going to think is, can I do a u-substitution? Probably not. It'll make it more complicated. Let's just look at this as sine x times sine x dx, right? Deal? Okay. Now let's try and do di. It doesn't matter which one I choose because they're both the same, right? So now let's take, this will be a cos x. If I integrate this, this will be a minus cos x. If I integrate this, this will be a minus sine x. And if I integrate this, this will be a minus sine x, right? So far, so good. Now I see that I've repeated the same function twice, so I'm going to stop. So that means this is equal to minus sine x cos x. Okay, minus sine x cos x. And then I take the derivative, or I multiply these two together. So I'm going to get plus sine x cos x, right? Plus sine x cos x, plus the integral of sine squared x, And guess what? Oh, how fun. This didn't get us anywhere, did it?
I think this one requires a trig identity.
Okay. So since that didn't
Maybe,
work,
I
I think what you might want to do instead is then probably take it as 1 minus cos squared u du. Or what was it? Oh wait, no, wait, hold on. We did sine squared. We were doing sine squared x, right? So do you want to? What would it be? Do you use your power reducing identity? Probably. What is it, like 2 sine x cos x? I forgot these identities. Is that what it is?
I think so.
Okay, so if that's the identity, you once again. Can someone confirm that for me? Can someone search that up real quick? I don't want to like do the problem wrong. The other option might be to do 1 minus cos squared x, but I don't think that'll help you.
I think that 2 sine x cos x is for sine 2x.
Okay. Is there a power reducing formula, like what sine squared of x is?
I mean, there's half angle identities, but I don't know. I think you're supposed to use the
Pythagorean?
Yeah.
Okay, let's think about this then. 1 minus cos squared x dx. If I wanted to, I can look at this as the integral of dx minus integral of cos squared x dx, right? If I viewed that as 1 minus sine squared x dx, would that help? No, that would not help.
Wait, is this how you're supposed to do it? I'm not sure.
I don't know. I don't think so. This doesn't seem to be working. This might be one of those integrals that you just can't solve analytically.
No, there's an answer. You can check the answer key.
Oh, is it part of the integration by parts problems?
Yeah.
Oh, which
I think
number?
it was. Wait, I'm not sure, but I thought it was. I did it like in class, I remember, in a breakout room.
It's right here. Number 8. Oh, I know. I think one way to do it might be to say u equals sine x, du equals cos x, correct? Dx. And then you take this to be integral of du over cos x is what? Sec x dx. So you'd have sec. Would that help? Because then that would be a u squared. And then dx would be du over cos x, which is sec x du. But I don't think that would help, would it? Or the other option is just to take the function as 1. Let's just try that. We might have been missing the easy function, or easy way all along. This was a di plus minus plus minus. Let's take this to be sine squared x. And let's say this was a 1. I don't know if this will help.
I think we did it wrong the first time.
Oh, the very first time that we did it?
I think so. It looks, didn't we get like plus the integral of sine squared x or something?
This is what you would have done, right? Sine x, and it would have been cos x minus sine x. This would be minus cos x, and this would be minus sine x, right? So if you do this, you'll get minus sine x cos x.
Maybe you're not supposed to do it that way.
Then how would you do it?
Apparently, sine squared x equals 1 minus cos
Cos squared x.
2x. 1 minus cosine of 2x all over 2.
Wait, you're supposed to just do it the normal way. It works out if you do that.
What we're doing right now
No, like the method she taught us in class.
with, what would you take u as?
U is sine x and dv is also like sine x dx.
That's what we're doing, the same thing.
Yeah, but somehow the answer is different.
That means I'm doing the math wrong somewhere. Okay, sine x, integrate sine x and you get minus cos x, right? Integrate minus cos x, you get minus sine x, right? We have a repeat so we can stop. Sine x, this is derivative is cos x, that's the derivative is minus sine x.
But with what you're doing, you'll just get the integral of sine squared x equals the integral of sine squared x. Do you see that?
Minus sine x.
Because you'll get negative.
Yeah, I
sine
see
x
what you're
plus
saying.
x.
And then you'll just get the plus integral of sine
Yeah,
squared
so
x.
it just like becomes the same as it
Yes.
was.
Okay. So I know I ran into this problem because I remember I did this. I was like, why isn't this working? Let me take a look at what I did real quick. And then this was which one? Number interesting. Okay. I actually stopped at just here. Why did I stop here? I didn't even do I just did sine x. All right, see, I got them. So I did cos x here, and then I did minus cos x here, right? Yeah, I did that. And then I just directly took it and I said, this is minus sine x cos x plus the integral of cos squared x, right? Dx. And then you need to say minus sine x cos x plus the integral of cos x, cos squared x dx is integral of 1 minus sine squared x dx. You can break this integral up into minus sine x cos x plus integral of dx minus integral of sine squared x dx. And now you can add this back to the other side, so you'll get a 2 here. And integral of dx is just x, right? And then you divide both sides by 2 plus c, and then that's your answer. Yeah.
So why did you stop after just
That's a good question. This is one of those where you just, this is another special case, I guess you could say. And this is where the DI method, I guess, has shortcomings. Is you would have generally stopped afterwards. But then you just have to think, okay, how can I solve this problem? Because if I had done another step, then I would have, like, things would have canceled out and it just wouldn't work, right? So instead, then you have to think, I'm just going to stop here instead. And that's something, it's one of those special cases. It's just one of those problems you have to do, and then, you know, now you know. Usually this doesn't happen though. Like, this is the only type of, yeah, and all the other ones, I didn't have any issues like that. Let's try number 6 real quick, and then we'll move on from this, because I feel like that's one of the complicated ones, I guess, you can think about. Yeah, let's try number 6. Okay, if you take, let's use our DI. We'll do a plus minus, plus minus. I cannot integrate arctan x, right? I just can't do that. So I'm going to put arctan x here. All right, let me look at the chat. All right. Okay, so arctan x here, and then let's put a 1 here. If I integrate arctan x, I'm going to get 1 over 1 plus x squared, right? If I take the derivative of arctan x, I get 1 over 1 plus x squared. If I integrate this, I'm going to get what? X, right? Now I can actually I can actually integrate this, and I can say this is equal to x arctan x, because I did my diagonal, and then I do a minus integral of x over 1 plus x squared dx, and now I'll have to do a u substitution basically, because I'll have to do a u substitution, but I can do this in my head, but just to show you guys, this is 1 plus x squared. Take u to be 1 plus x squared. Du would be then 2x dx, but I'll just divide the 2 here, and then you'll have x dx, right? And this is why u substitution here works, because think about it, that if I take the derivative of the bottom, I get the top dx. So that's why u substitution works. And if I wanted to take the integral of this, this would be x arctan x minus 1/2 ln of 1 plus x squared. And since this is always positive, you can print parentheses around it instead, plus c. Okay, so it's still integration by parts, but you just have to do that u substitution in there. If you're more comfortable using u, du, v, dv like we did in class, that's fine too. You're doing the same thing. This is just, it just saves time because you're not writing out u, dv each time. Okay, it's just a faster way of doing it. Okay, all right, I think we're good with this. Let me go ahead and clear everything here. All right, I think Maham said she wanted to do some of the net change problems. Partial fractions is not going to be on the test, right? She said it won't be on the test, partial fractions.
Yeah, I don't think it's gonna be on there.
Okay. And then Ftc and Mvt is just, that's something you'll do by word problem. So if you understand, yeah, this is Ftc actually. So, all right, which one?
It was question 3, I think.
Question 3, this one? Oh wait, no. This one.
Yes, yeah.
This one?
Yeah.
Okay.
It's just weird. I don't know. There was just some times where finding delta x like with the b minus a over n, that's not what found delta x. It was actually
it's because you're doing a trapezoidal sum here. When you're doing trapezoidal sums, there's no need to use the summation form.
Oh, okay.
You understand what I'm saying? You can just take, the base and then think of it like that, and then draw your trapezoids.
Okay. There was one, I'm trying to remember. Shruti, do you know which other one like we had that problem with? There was, I can't remember, but there was one more that we were like the delta x formula doesn't work for it. It's probably another trapezoidal sum one then. Yeah, I can't find it. It's okay. Yeah, it's fine.
Okay. Before we ended, I just wanted to do one random word problem that I've never seen before, that you've probably never seen before, from the 2018 BC Calc exam, just for practice, because, Okay. Okay. So these are calculator. You must have a calculator for this section. This is a derivative. Oh, we actually did this. This was one of our test questions. You remember this? A grain is being added to a silo. Or did we not have the same question? I remember this was on one of our tests this year. This was actually just a derivative problem. And this one used right Riemann sums, but so there's no need to do this one. Let's just move on to the next problem. Why can't I scroll down? There we go. We did this. No need to do this again. This is parametric, and we haven't learned to do that, so no need to do that. Sorry, I have to find a good problem to do. If you guys find a problem, we can do that. I think we did this problem as well, right? Did we do this problem somewhere? This one looks familiar. Okay, why don't we do this one? I think this is a good problem to do. All right. The function g is defined on the closed interval here. The graph of g consists of two linear pieces and a semicircle. let f be the function divided by f of x equals 3x plus the integral from 0 to x of g of t dt. Find f of 7 and f prime of 7. Okay, can someone walk us through this? Does someone want to try walking us through this? I think you'll benefit if you try, even if you get it wrong. Anyone? Rishi, do you want to try? Zachary, do you want to try? Anish, maybe? I don't know. Anyone? Okay, that's fine. I'll go. So we're trying to find f of 7, right? So f of 7, we can just use our definition of the function, which is it's 3 times 7, which is 21, plus the integral from 0 to 7 of g of t dt. Well, I can just think of the integral of g of t dt as the area under the curve, or the net change of accumulation from 0 to 7. So I'm finding the area from here to here. So I have 27 plus 0 to 7. So what's the area from here to here? I know it's pi r squared over 2 because it's a semicircle. R is 1, 2, 3. Pi r squared would be 9 pi, correct? 9 pi over 2 is 4.5 pi. Or I can just, if I want to be precise, I can write 9 over 2 pi. Plus the integral from here to here. Well, that's just a rectangle. Actually, this was a minus 9 over 2 pi. I'm sorry. This was a minus 9 over 2 pi, right? Because it's a negative area. If you want to think of it that way. And then the area here is 1 times 1, 2, 3, which is 3. So plus 3. So this is actually equal to 30 minus 9 over 2 pi. That's f of 7. Now, what about f prime of 7?
Hold up, MG, how did you get 27 initially?
Oh, 21. I'm sorry. That's a 21, correct? Because it's f of x equals 3x plus 0.
Okay, I got 21.
Okay, you got 21. I'm sorry about that.
That's not good.
And that would have been 24. I think so. Yeah, 24. Okay. So now let's figure out f prime of 7. So using our definition of up here, if I have f of x, if I differentiate both sides, what am I going to get? I'm going to get f prime of x equals 3 plus, if I differentiate with respect to x, this function, what am I going to get? I'm just going to get g of x, correct? You guys see that? Because if I take d dx of the integral of 0 to x of g of t dt by fundamental theorem of calculus, we know that this is just equal to g of x. Okay, so now we know that f prime of x equals 3 plus g of x. That means f prime of 7 is equal to 3 plus g of 7. G of 7 is what? Positive 3. So it's 3 plus 3. That means f prime of 7 is 6. Okay? All right, next question. Unless you have any questions on that.
I have like just one really quick question.
Sure.
What is the exact meaning? Like, what is the meaning of like when an integral, the upper boundary is less than the sorry.
Good question. Great
less than
question. Okay. It just flips signs. So sometimes it's like double thinking and you have to like, it's kind of weird, but let's think about the integral from 0 to 6 of g of x or gt. I have to use, actually, we can use g of x here. G of x dx. The area is 9 pi over 2, right? But it's negative 9 pi over 2. If I had taken the integral from 6 to 0 of g of x dx, then that would have been positive 9 over 2 pi. Because from here to here, you're accumulating negative, but from here to here, you're accumulating positive, because if you think about it, you're going in the reverse direction, so it's accumulating positive over time. Okay, so you just flip the sign. So if I had taken the integral from -4 to 0, then it would have been positive. Or if I had taken the integral from 0 to -4, it would have been negative. Okay, all right. Same value. Okay. Find the value of x in the closed interval -4, 3, at which f attains its maximum value. Okay. When will f attain its maximum value? Forget what the question is asking. When does f attain a maximum value? We learned this in first quarter, right? Maximum and minimum values of a function. When does a function attain its maximum value? When f prime of x is equal to, anyone?
It's when it equals 0.
Yeah, when it equals 0, and before the interval, f prime of x is greater than or less than 0. Before that point. So say that this is my maximum value. Is f prime of x greater than or less than 0 here? Left at that point. Greater than 0, right? And then afterwards, f prime of x is less than 0. So if we look here, from -4 to +3, right? It's only asking about this interval from -4 to +3. When does f prime of x equal 0? Well, we know that f prime of x is equal to 3 plus g of x, correct? That means f prime of x, we want it to equal 0. So now we need to think, when does 3 plus g of x equal 0? That's when g of x equals -3. When does g of x equal -3? That's at +3. That means x equals +3. Now we need to confirm that this is a maximum value and not a minimum value. How do we do that? We go back and say f prime of x equals 3 plus g of x. Let's calculate something just to the left of that, and we need it to be greater than 0. So let's say g of 2. G of 2 is, let's say it's like -2.75. 3 minus 2.75 will be positive. Check. And if I do something like 4, then I have minus 2.75. 3 minus 2.75 will also be positive. So it'll actually be like this. So is that a maximum value then? No, it's not a maximum value, is it? Yeah, unless I did my math wrong. I might have done my math wrong. Is f prime of x equals 3 plus g of x? Yeah, and then g of x would have, when does g of x equal -3? That would have been when we have a derivative of 0, but to the left of it, the derivative is increasing, and then also to the right of it, the derivative is increasing. You see what I'm saying, guys? And it says find the value of x at which f attains its maximum value. So then when does it attain its maximum value? It can't be here. It's not when f of x equals 0. That means it has to be one of the endpoints, correct? And that's my extreme values theorem. That means it has to be one of the endpoints. So from -4 to 3. Oh, whoops. So that means from where we have -4 from negative, what is going on? Okay, okay, what is, huh? Oh, okay, all right. So from -4 to +3, f prime of x will still be equal to 3. Or actually, we can just think about f of x. F of x equals 3x plus the integral from 0 to x of g of t dt. Let's think about f prime. That means we figured out already that our critical point it doesn't work at our critical point, does it? It doesn't work, right? We didn't check it. There was another critical point that we didn't check. Can someone point that out? When does g of x, when does this not exist? It doesn't exist at x equals 0, right? So let's try and plug something in here. G of -1 is, or let's try g of -2. That would be +1. 3 plus 1 is 4. And then g of, let's say, 3 is what? G of 3 would be -3. 3 minus 3 is, or let's try something else. Let's try g of 2. It would still be positive. So we have another saddle point here. This isn't a maximum either. Okay, So actually, based on this, we can draw a conclusion, because what we just showed was that f is increasing from here to here. We have a derivative of 0 here, or it doesn't exist, or something like that. Then we're also increasing from here to here. So we have something like this, and then something like this. So this must be where our maximum is. And the way you would mathematically show that is just simply by calculating f of x at your critical values of -4, 0, and 3. Okay? And you could just plug in f of x. Let's check our answer for that one. I just want to make sure. I think it would be x equals 3, and then you would plug in x equals 3 and get the actual maximum value. Yeah, x equals 3, right? Because f prime of x is greater than 0. Like we said, remember we just said it's positive, right? They're using the same justification. Good. Did we get these right? I think so, right? We got the first number 1 and number 2 right? Okay. Let's go back to our questions. Let's just finish up that question, and I think we'll call it a day unless you guys have any more questions. Okay. We did B. For each of limit x approaches 0 negative of g of prime of x, and then positive, find the value or state that it does not exist. So we need to find the limit as x approaches 0 from negative of g prime and then from positive of g prime. Okay. So we have g of x. We need to find g prime of x. G prime of x from the negative side is it defined? From the negative side, g prime. I'm thinking about the slope, not the value. G prime of 0 is definitely not defined. But, and we're not asking about g of 0 either. Remember, it asks about g prime of 0. For g prime of 0 from the negative side, is it defined? Yes or no? It is defined because it's a negative number. It's -1. It's a constant value. It is defined. I know at g prime of 0 itself, it's not defined because you have a point, sharp point here. But the left-handed limit of the derivative does exist. What about the right-handed limit of the derivative? That doesn't exist because it's a vertical tangent. So what you would say is left-handed derivative is -2 over 1, 2, 3, 4. So it's -half is the left-handed derivative, and the right-handed derivative does not exist. You understand what we did there? How that worked? And this is derivatives again, but still, you need to know this, right? Okay. And then find the limit as x approaches -2 of 3x plus 6 minus 3 to the x plus 6 minus 1, and on top f of x plus 7. I don't think we're going to do this one just because. All right, no problem, Manish. Thank you. This one is not really. Do you want to do this one or no? We don't have to. Okay, yeah. That's. You can find more of these free response if you'd like online. They're really helpful, but that's pretty much it for what I have. Do you guys have any other questions? Any other questions? Yes, no?
Okay, I just want to check. So there will be so indefinite, definite integrals, then f-talk, MVT,
Yep.
and then we'll have.
Oh, sorry, I forgot to mention MVT. Average value of a function is 1 over b minus a times the integral of that function from a to b. Simple, right? Just remember that. Make sure you remember that. That's the average value of a function. Okay, sorry, Karen, go ahead.
No, yeah, I was just listening. And then we have integration and then net change. That's the
net change, yes. And just remember, net change means that's what the fundamental theorem of calculus states. I start off with f of some number, and then to calculate what f of some number c is, then I need to find the f of 0, or I need to find some sort of. Do you see what I'm saying? Let's look at this visually real quick. If this is the rate of change of something, right? This is the rate of change of something, and I tell you that this is f of x. Let's say this is f of x, and this is the rate of change that people walk into a bar. Okay, people walk into a bar at this rate. That means the number of people in the bar is capital F of x. And if I tell you that f of x if I tell you what let's say I tell you f of 3 is actually equal to 50. That means there's 50 people at the bar, and this is 3. That means capital F of x is equal to f of 3, which is 50, plus the integral from 3 to x of f of t dt. This is what you need to remember. Think about it visually. What I'm doing is I'm starting off at a certain value, like f of 3 is 50. Then what I'm going to do is take the net accumulation of change from that x value to whatever this way or this way. And remember, Maham, like I said, here it's all positive. So if you actually went from 3, if you went from 3 to like -1, or is 3 to 0, let's just say 0. From 3 to 0, then it would actually be negative. And that would make sense, right? Because as time goes on, more and more people walk into the bar because the area under the curve is positive. More important people walk into the bar. And if I go from 3 to -1, if I wanted to find f of 0, let's say, then it would be less than 50. It would still be positive, but less than 50. Actually, it might even be 0, depending on what our initial condition was. Okay, so now that's all net changes. It should make perfect logical sense, right? Because you're starting at a value and you're either adding the accumulation or subtracting the accumulation, or a combination. Okay. Kern, anything else?
No, that's good. I just wanted to summarize.
Yeah, sure. No,
Thank
that
you.
was good. That was good. Zachary, anything? Trudy, Maham. All right. Thank you all for attending. I mean, this was pretty long. It's been almost 2 hours, but hopefully you found this helpful. And I know this. I mean, just going through it with you guys really helps me. So thank you guys. Yeah, and as always, if you have any questions, put it in the Slack. We can text each other and we can figure it out. Okay.
Yeah. Thank you, MG, so much.
All right. See you guys. Bye.
Thanks, MG. See you.